Okay, this is review over the last half of Friday's lecture from last week and Monday's lecture from this week. He started out with Introduction to Solutions. That was pretty self-explanatory. I kind of made some notes, the how a real solution, the solute is divided on a molecular level. I kind of drew a picture for myself of what I think it is. Somebody can correct me if I'm wrong. I think that the other two that he talked about, the colloidal or colloidal, however you say that, and coarse dispersion means that maybe it's not separating to a molecular level like it did over here. It's kind of staying bigger. Oh, where did I just jump to? I have so many computer problems when I do this. There we go. But they didn't separate, so they're bigger. So it's technically in two phases, like it could be in solid and in liquid. It's not just liquid. Would you agree on that, Joe?
Mm-hmm.
Then he talked about solute and solvent. We've seen that a million times in our undergrad. Definitions of them. We know that stuff. On the colligative, I just made some notes. This property, it's only due to numbers. So 1 mole would always equal 1 mole and stuff like that. The additive is when you like calculate stuff, like calculating atomic weight. And then constitutive is stuff like solubility. No matter the amount of drug, it'll have the same solubility. So those are some properties that he described that we can use to describe solutions. Skip down non-electrolytes and electrolytes. He did mention that we need to memorize the electrolytes, the weak and the strong, and he won't be using any that he didn't mention to us in this PowerPoint. So memorize that urea and naphthalene is non-electrolyte, and memorize the strong and the weak for the quizzes because we'll have to know them.
And sucrose and glycerin.
Sucrose and glycerin. Yeah, was that in the Word doc?
Electrolytes. Yeah.
Sucrose is a non-electrolyte, right?
Yeah. Sucrose, glycerin, naphthalene, and urea. Urea were not electrolytes.
Yeah, so there's 5 total there that we need to memorize because he said there's no way to tell the difference, just memorize it, and he won't ask anything that's not on here. These are the ones that I thought might be difficult for people. It may have been a while since you've seen molarity. So I worked out the problem, and here's some notes. If you need 1 molar solution of NaCl, you will weigh out 58.5 grams of it and mix it with 1 liter of water, or the more sufficient way to do it to where it's more accurate, you would put your 58.5 grams of NaCl in a graduated cylinder or something that would measure up to 1 liter, and then quantity sufficient up to 1 liter would be more accurate, is what he said, instead of just measuring 1 liter and dumping it in there, because then you would end up with a little bit more. And here's how I solved for molarity. I did a calculation where I converted the 10 grams into moles, and then I just divided that by liters, which I converted the 100 mils into 0.1 liters and divided it. If anyone has questions on that, we can meet on link. That one's pretty simple. Equivalent weight, I feel like, might be the most difficult part of this. If you've never worked with milli equivalents, you will work with it a lot in pharmacy, particularly potassium. If you don't work in a pharmacy, or if you do, I'm sure you've heard of like the potassium 10 milli equivalents or 20 milli equivalents. You will see that a lot. His example here was human plasma contains about 5 milli equivalents per liter of calcium ions. How many grams are required to prepare 2 liters of a solution equal to calcium? So the first thing I did was right over here was I figured out what am I going to divide by. I have 1 calcium in there, and I know from past experience that calcium is a positive 2 charge. We should probably go back and memorize these if you don't know them. Know that calcium is a positive 2, chlorine is a negative 1, and look for other ones that he's mentioned in the PowerPoints or the Microsoft Word and memorize those too, because I'm sure he will ask us about it and he will not tell us the charge of those. So to figure out what a gram equivalent is, I took 147, which is the total weight, divided by 2, and I got my 2 from this up here. If I would have had 2 calciums, then it would have been 4. But in this equation, you can see I only have 1. So if anybody's wondering where I got that 2 from, that's how I got that. And in case anybody's curious as to why in the heck are we dividing 147 by 2, I'm doing it because I want to know how many grams of this calcium chloride with water contain 1 equivalent of calcium ions. So 1 gram equivalent is 73.5 grams, if that makes sense. So if anybody's wondering how he went from right here to right here, I just did conversions and divided it. So 73.5 grams, you move the decimal over 3 places, and now we have that many milligrams. And I did that the same way with gram equivalents. I changed it to milliequivalents, so I had to move the decimal 3 places. And then I just divided, and it happened to be the same number. 73.5 milligrams is in 1 equivalent, milliequivalent. So now we move on. I need 2 liters of 5 milliequivalents per liter. So how many milligrams of my calcium chloride do I need? Well, to figure out, I know that I have 73.5 milligrams in 1 equivalent, but I need 5. So I take 73.5 and I multiply it by 5, and I get 367.5 milligrams. But that's only for 1 liter, and I need 2. So I take that 367.5 milligrams and I multiply it by 2 to get 735. He made this all one step when he did it, and I kind of separated it out so people could understand why we're multiplying what by what. The way I learned how to do it, and I think it's a little bit quicker, is I just do a conversion. I know that I need 2 liters, and if there's 5 milliequivalents in 1 liter, then I know there's 10 milliequivalents in 2 liters. So then I just take my 735 or 700 or 73.5 milligrams per milliequivalent and I multiply by 10 and I get the same answer. He gave us another example. Well, he said, what if I just wanted half a liter? I could do that using my quicker way also. If I knew that I had 5 milliequivalents per 1 liter and I needed half of that, then I could just divide both of these by 2 and I get 2.5 and 0.5. So then I would multiply my 73.5 by 2.5 and it would give me my answer. If you guys prefer his way better, I can work with somebody on that. Otherwise, I think this is a little bit faster than multiplying it twice. That all makes sense, Joe?
Is there always, so 5 milliequivalents?
Uh,
I know that was given, but 5 milliequivalents per
it won't always be 5 milliequivalents. Like it could be 20.
always be 5, but it'll always be per 1 liter.
Yeah, because over here he put human plasma contains 5 milliequivalents per liter. So they'll give you like a standard, and then they'll tell you what they want.
Okay.
So up here, it's understood that it's a liter. Like if that was 20, say that was 20 milliequivalents per liter, then we're just going to imagine here. Let me change my pen color. Say it was 20 milliequivalents per liter.
Hold on real quick. You see that little top double arrow on the top right next to add page?
Huh?
Yep, click that.
Is that what you wanted? It bigger?
Yep.
Okay, cool. Thanks. I didn't know I could do that. So on my, say I was working with 20 milliequivalents per liter instead of 5 milliequivalents per liter.
You need to drag your screen over now.
Oh, can you not see it?
Sorry. Oh, I see it. Never mind. Yep.
I was writing in blue.
Yep.
Okay. Let me know if I write off the page again. I thought you guys could see my whole screen. Oh, there's my alarm going off. Sorry. Okay, anyways. So I know I need 2 liters. So to get from 1 to 2, I multiplied by 2, obviously. So I'd multiply this by 2, so that'd be 40.
Okay.
So then I would replace this with 40 right here and multiply across. That's the easy way to do it. Up here, I would replace my 5 with 40.
Yep.
So either way, if anybody wants me to go over it in more detail, just message me on link or Facebook and we can have a little one-to-one session. Normality, he didn't really go over this, so I worked it out by hand because he kind of said it was self-explanatory. I thought it might be a little complicated for those who still weren't comfortable with the gram equivalents or milliequivalents, so I did the problem here. He said, what is the normality of a solution containing 10 grams of sodium chloride in 100 mils of water? when the atomic mass of sodium chloride is 58.5. That's a constant. So what I'm solving for is this right here. So to get to that right there, I know I need to divide and get my milliequivalent out. Once again, I calculate what number I'm going to divide by. I know that I only have one sodium in my NaCl, so I wrote 1 Na, and I know it's just a positive 1, so I'm only going to divide by 1, so my number didn't even change this time. So I have 58.5 grams of sodium chloride equals 1 gram equivalent. So now I need to convert this to milliequivalent. Well, let me see here. Oh, I need to convert it using the 10 grams that I was given. So I took 10 grams and divided it by 58.5, and I set it up like this so you guys could see how the grams canceled out. So my 10 grams of sodium chloride has 0.17 milliequivalents. Does that make sense so far?
So that would be 0.17 gram equivalents, and then that would be
Oh yeah, I wrote milliequivalents. Sorry, that is supposed to be a gram. I'm so used to writing MEQ. I've never used.
one. Isn't 0.17 gram equivalents equivalent to 0.17 milliequivalents?
No, I think no, because I was up here. I got my 50 there. I got my total of 58.5 grams in 1 gram equivalent. So I used it down here to convert to, or to figure out how many milliequivalent, or sorry, I keep saying it. Sorry, how many gram equivalents is in 10 grams of sodium chloride. So I calculated that. Does my calculation seem confusing?
No, yeah, no, I got it.
Okay, yeah, and I accidentally wrote an M over here because I've never used a gram until now. So like my hand just automatically puts MEQ. Sorry, guys. So now I know that I have 0.17 gram equivalents in 10 grams of sodium chloride. So real quick, I convert my 100 mils to liters because they gave it to me in that, and then I just divide it because normality is gram equivalents per liter. So I just took 0.17 divided by 0.1 and I got 1.7 for normality. And that's what he got. Did that make sense, or do you want me to go over it again?
No, I just like the previous problem, the gram equivalence was equal to the milli equivalence.
That was because, here, I'll go back up there. It's not really equal to it, because if you look right here where I converted, I said, now let's convert milligrams in milliequivalents, because I started out with 73.5 grams, and I converted that to milligrams, because I moved the decimal over 3 times.
Mm-hmm.
And 1 gram equivalent equals 1,000 milliequivalents.
Mm-hmm.
So to figure out how many milligrams per equivalent I had, I just divided these two numbers by each other. And when you divide 73,500 by 1,000, you get 73.5 milligrams per milliequivalent.
Right. So, oh yeah. So we were because it's grams per.
That's why it's the same. I mean, the way he wrote this, like one person could, like someone could almost look at that and think, oh, so, because this almost looks like 73.5 grams equals 73.5 milligrams. That's not the case. The way he wrote that is kind of confusing. That's why I went and did the conversion and reduced it. So.
Because I felt really stupid for about 5 minutes there.
Yeah, no, that's what took me a while, and that's why I worked this all out. Because when I first saw this, because like I said, I've never worked with gram equivalents before, and when I looked at this, when I was like, which means 1 gram equivalent, and therefore this, and I was like, what? How is that the same? How is milligrams the same as grams?
Didn't
And
I didn't catch it. He was saying 1 gram equivalent is equal to 73.5 grams. Should that would mean that 1 milli equivalent would be equal to 73.5 milli equivalents. Yeah.
yeah. So that's why I kind of drew that out. And yeah, because that threw me off hardcore too. I was just like, how is that the one and the same? I didn't understand it. But then once I wrote it all out and reduced it, I was like, oh, that's why, because 73,500 divided by 1,000 is still the same number.
Yep.
So that's why over here, and that's one thing we got to watch out, guys, like pay attention to what he's asking for, because I mean, I think normality is always going to be gram equivalents per liter, whereas when we're solving for just plain equivalents and stuff, he may be asking us for milli equivalents, so we got to watch our stuff so we don't have a decimal in the wrong place and get the answer completely wrong, because I'm sure in his multiple choice he will be giving us both answers and we just need to know which one is right. So, do you want to move on or do we want to go over it again?
I'm good.
Okay. Molality, I went over that. Let's define it. That was moles of solute per kilograms of solvent, hence the kilograms. Watch that because that could mess us up, especially in this because he gives us 100 grams. This time he underlined it and he bolded it. I don't think he will do that in the exam, so make sure you change it to kilograms when you're solving for molality. Molality was pretty simple. I turned my 10 grams of sodium chloride into moles over here, and then I turned my 100 grams into kilograms, and then I just divided, and so my answer was 1.7 molal. Like I said, that's pretty simple as long as you remember to change everything into kilograms and moles. Otherwise, if you divide it by 100 grams, you will get the wrong answer.
So would E and normal C be the same number?
Hmm?
And it wasn't that question. I don't know if it'll be in necessarily all questions, but
Which one?
well, I guess it depends on how much.
Did you say E and C? What do you mean by E and C?
1.7 molal was the same thing as 1.7 in for normalcy.
Oh, yeah. Well, that's probably because we keep using 10 grams of sodium chloride. See, we use 10 grams up here,
Right.
which, 10 grams divided by 58.5 gave us that. So that was because our gram equivalents happened to be the same number as our weight since we only had one sodium.
Yeah.
Yeah, but I mean, if we were using something like calcium or something that had like a +2, then we would be dividing this by 2, and so our normality would have been different. But since we're dividing it by 1 up here to figure out our equivalent, it's all going to be the same.
Yep.
So, and then mole fraction, it's the ratio of moles of solute to the total moles present in the solution. One thing he did highlight on here is we have to make sure that we total up our moles. Let's zoom out a little so we can see everything. So, once again, we have 10 grams of sodium chloride, which after converting it a million times, I knew was 0.17 moles. And then I also had to figure out how many moles I had of water, which he gave us those. I'm sure he'll do that for the test since we can't have a periodic table. So 100 divided by 18 was 5.56. So in mole fraction, he said if it is not specified which mole fraction we're finding, if we're talking about sodium chloride or water, if it doesn't specify, then use the solute. And in this case, sodium chloride is the solute not only because we have less of it, but also because he said water will always be a solvent pretty much. So it's not specified, so I solved for sodium chloride. So I found my total moles by adding sodium chloride mole in water mole, and I got 5.73 moles total. So then all you do is divide your moles of sodium chloride by your total moles, and you get 0.029. And he did make a comment that when you are figuring out mole fraction, you won't have a unit. So no units on mole fraction. And then percentage expressions. One thing I wanted to talk about on this, you will use this a lot, especially if you are not a certified technician yet and you're thinking about becoming a nationally certified technician. These questions will be on your PTCB exam that you take, and you need to remember that.
Just a quick thing. Since we're all pharmacist interns, we don't have to be technicians anymore.
No, well, I guess true, not. Well, okay. I don't know what I'm used to helping pharmacy tech, sorry. But one thing I know that a lot of people struggled with when I was helping people prepare for that exam was they were trying when they wanted to, if they give you this and they say what is the percent weight per volume, people were taking 10 and dividing it by 100, and that is wrong because if you take that divided by 100, you're going to get a decimal like 0.1 or something like that. I don't do math in my head, but like you're going to get 0.1, and that's not the answer. Your answer would not be 0.1%. It's going to be 10%. So remember, if it just says 10 over 100, then it's 10% weight per volume. or weight per weight. And if it's 10 over 100 and they tell you to convert that to weight per volume, just take that top number and put a percentage on it. Do not divide anything. I've seen people try to do that before and they get the wrong answer, so don't do that. And then let's see here. Last thing he talked about was osmotic pressure. That should be a review. If not, don't hesitate to ask. I will not make fun of anybody for asking because I realize that for some of you it's been a while. So if you don't understand that, ask me. One thing Joe and I were just discussing before we started recording this was how hypertonic and hyperosmotic are pretty much one and the same. Like when he's describing it here, he's saying hyperosmotic solution or higher osmotic pressure, the red blood cell will shrink. That's the same for a hypertonic solution. Everybody knows that if we throw a red blood cell, into a beaker that's hypertonic solution, then, stuff is going to go rushing out of the red blood cell trying to reach equilibrium and it'll shrivel up. Same goes for hypotonic. If you throw a red blood cell into a hypotonic solution, then everything is going to rush into the blood cell trying to reach equilibrium and it'll swell and burst. Somebody can correct me if I'm wrong, but isoosmotic and isotonic are not one and the same. They are different. What I gathered when he was talking about it, and what I gathered from reading about it, is if you're talking about an isotonic solution, that means that the concentration of water is the same, the concentration of ions is the same, everything is the same. So there's going to be like no rush movement between stuff. Stuff will move freely in and out, but it will be at equilibrium. So the red blood cell will not change. When you're referring to isoosmotic, osmotic refers to water only. So when you're talking about an isoosmotic solution, that means the concentration of water in the blood cell and the concentration of water in the surroundings is the same. Isoosmotic does not refer to ions or anything else like that. So isoosmotic could have the same concentrations of water but different concentrations of ions, which could move across the membrane in the red blood cell and cause it to change shape. So just wanted everybody to know that. I think that's what that means. I haven't looked into it too much, and I'm sure he's going to go back over it. So just remember that isotonic and isoosmotic are not the same, and hypertonic, hyperosmotic are the same as hypo. So is there anything that you think I missed, Joe, or anything you want to throw in there?
I think just for clarification, it has this hyperosmotic and hypertonic and hypoosmotic and hypotonic have the same result but for different reasoning.
Yes, that is very true. Do you want to explain that, or do you want me to explain that?
If it's hyperosmotic, that means the water pressure is different on inside the cell versus the outside the cell. Hypertonic would be the ion concentration is different on the inside of the cell versus the outside of the cell. Both will result in the cell shriveling and dying, but for different reasons. And same but opposite for hypotonic or hypoosmotic solutions.
Yes, that's a good point. Yeah, tonic is ions or other things like glucose or something, and osmotic refers to water. So, all right, I don't think there's anything else.
Nope.
All right, guys, I hope this helps. Let me or Joe know if you have any questions. I'm gonna stop recording.